The Milky Way is 10 billion years old. Even at 1% of the speed of light, a civilization could cross it entirely in 10 million years. That means any civilization that arose more than 10 million years ago and survived should already be everywhere, in every star system, on every planet, impossible to miss. And yet, we have been listening to the sky for 66 years with the most sensitive instruments ever built, and we have heard nothing. Not a whisper, not a signal, not a single confirmed sign that anyone else has ever existed anywhere in this galaxy. The universe is not merely quiet. It is quiet in a way that the mathematics says it should not be able to be. Tonight, we find out what that silence is actually telling us, and why the answer might be the most important thing our species has ever heard. If this kind of journey moves something in you, taking a moment to like this video and subscribe is the quietest, kindest thing you can do for this channel, and it means more than you know. Go ahead and settle in somewhere comfortable. In 3, 2, 1, liftoff. It was a summer morning in New Mexico, and the air above Los Alamos smelled of high desert and pine. The year was 1950, and the men walking to lunch that day had already changed the world once. They had split the atom, built a reactor under a football stadium, and watched a fireball rise above the Trinity test site not 5 years earlier. Now, some of them were back, reassembled at the laboratory in the Jemez Mountains to work on something even more powerful, and the ordinary business of lunch, the walk across the grounds, the smell of food, the easy conversation between colleagues was the only truly quiet thing left in their lives. Enrico Fermi was among them. He was 48 years old that summer, though he seemed in some ways to belong to a different order of human being than the men around him. He had won the Nobel Prize in Physics in 1938 for his work on nuclear reactions induced by slow neutrons. On that particular morning, he was walking to the Fuller Lodge for lunch with 3 colleagues, Emil Konopinski, Edward Teller, and Herbert York. Konopinski was a nuclear physicist who had studied the structure of the atomic nucleus and contributed to the Manhattan Project. Teller was already famous, a Hungarian-born physicist who had worked on the hydrogen bomb and would go on to become one of the most controversial scientific figures of the century. York was a visiting physicist from Berkeley, joining the group as they crossed the grounds. The newspapers were full of unidentified flying object reports that summer. The country had been gripped by sightings since the summer of 1947, when a pilot named Kenneth Arnold described seeing 9 bright objects flying at extraordinary speed near Mount Rainier in Washington state. And the press coined the phrase flying saucers to describe what he claimed to see. By 1950, the public interest had not diminished. Konopinski had recently noticed a drawing published in the May 20th issue of the New Yorker magazine. It showed little green men with antennae loading trash cans from the streets of New York City into a flying saucer. They were still laughing when they sat down for lunch. The conversation moved on. It turned. They were having lunch and casually talking about UFO sightings when Fermi suddenly said, "Where is everybody?" On the one hand, everything we know about the universe, its age, its size, the prevalence of stars, the abundance of planets, strongly suggests that intelligent life should have arisen many times over in the Milky Way alone. On the other hand, every observation we have ever made, every telescope we have ever aimed at the sky, every signal we have ever searched for, returns the same answer: nothing. Silence. An emptiness so total and so complete that it is itself the most important data point in the history of astronomy. To understand why the silence is so disturbing, you first have to understand the scale of the opportunity. The Milky Way galaxy is approximately 10 billion years old. It contains somewhere between 100 and 400 billion stars, depending on how you count the faint, dim red dwarfs that far outnumber everything else. Modern exoplanet surveys, particularly the data gathered by NASA's Kepler Space Telescope and its successor TESS, have established beyond reasonable scientific doubt that planets are not rare exceptions in the galaxy. They are the rule. At minimum, 1 in every 4 Sun-like stars has a rocky planet orbiting in what astronomers call the habitable zone, the band of orbital distances where liquid water could exist on a planetary surface. When you extend that calculation across the galaxy's full stellar population, you arrive at a staggering figure. Conservatively, tens of billions of potentially habitable worlds in the Milky Way alone. Some estimates go higher, into the hundreds of billions, when you include the smaller red dwarf stars that make up the vast majority of the galaxy's stellar content. Now, consider the time available. The Milky Way has had 10 billion years to produce, nurture, and exhaust its stars. The Sun is just under 5 billion years old, making it a middle-aged star by galactic standards. That means there are stars in this galaxy that finished burning hydrogen and collapsed into white dwarfs before the Earth even formed. There are planetary systems in this galaxy that are 6, 7, 8 billion years older than our solar system. Whatever life may have arisen on those worlds had billions of years more than us to develop, to learn, to build things, and to reach outward toward the stars. Here is where the paradox sharpens into something that is genuinely hard to dismiss. You do not need faster-than-light travel to colonize a galaxy. You do not need any physics that violates what we currently understand. At just 1% of the speed of light, a modest velocity that represents a fraction of what current theoretical propulsion concepts could in principle achieve, a spacecraft could travel from one stellar system to a neighboring one in a few hundred years. That civilization could then establish a colony. That colony could, after a few generations, send out its own expeditions to neighboring systems. And those colonies could do the same in a process that spreads outward like ripples on an enormous, slow-motion pond. The mathematics of this expansion are well established. Even accounting for the vast distances between stars, a civilization expanding at this unhurried pace could colonize the entire Milky Way in roughly 10 million years. 10 million years. It is an almost inconceivably long time by human standards, longer than the entire history of the genus Homo, longer than the time since our ancestors first walked upright on the African savanna. But, on the scale of the galaxy's 10 billion year history, 10 million years is nothing. It is 0.1% of galactic time. It is less than the time it takes for the solar system to complete a single orbit around the galactic center. In the life of the Milky Way, 10 million years is a Tuesday afternoon. Any civilization anywhere in this galaxy achieved interstellar travel capability at any point in the last several billion years, and then survived long enough to do anything with that capability. We should be able to see its influence everywhere. Not just in a few star systems, but in all of them. The artifacts, the transmissions, the evidence of something having been there and having left its mark should be detectable by any civilization with a radio telescope and enough patience to look. The night sky should be alive with signals. Our own solar system should bear the fingerprints of visitors who came long before our world even existed. The fact that it does not, that the solar system is as pristine and unmodified and apparently unvisited as it was 4.5 billion years ago is not merely strange. It is, on the face of it, almost impossible. This was the insight that arrived over lunch in New Mexico in 1950, and that has never fully been accounted for in the 76 years since. Fermi did not frame it as a paradox. He asked it as a question, and then, by Teller's account, he concluded with the thought that the distances to the nearest living beings might simply be very great, and that we lived, as far as the galaxy was concerned, somewhere in the sticks, far from the metropolitan area of the galactic center. He was not convinced the answer was terrible. He was not certain the silence meant doom. He was only certain of the silence itself and curious about what it meant. The formal argument, the version that elevated the question into a true scientific problem, came 25 years later, when astronomer Michael Hart published a paper in 1975 in the Quarterly Journal of the Royal Astronomical Society. Hart laid out the logic precisely. If any extraterrestrial civilization had ever developed interstellar travel capability in the history of the Milky Way, it would by now have had more than enough time to colonize every habitable planet in the galaxy. The absence of any detectable extraterrestrial presence in our solar system therefore implies, unless you can construct a compelling reason why no civilization has ever done this, that no such civilization has ever existed. Hart's paper provoked a sharp response from the scientific community, and the debate has never fully settled. But it established the paradox in its sharpest and most uncomfortable form. What is particularly unnerving about this formulation is how little wiggle room it leaves. You might argue that interstellar travel is simply too expensive, too dangerous, or too unappealingly slow to attract any civilization's investment. But that argument requires every civilization that has ever existed across the entire 10 billion year history of a galaxy containing hundreds of billions of stars to have independently arrived at the same decision, not to do it. Every single one, even one exception, one civilization in the entire history of the galaxy that found a way and had the motivation to spread outward, would have been enough to fill the galaxy. The absence of even a single success is what makes the silence so strange. You might argue that civilizations inevitably turn their attention inward, toward virtual realities or spiritual development, or problems so consuming that they abandon any interest in expansion. But again, every single one, without exception, for the entirety of galactic history, you might argue that the distances are simply too great and the stars too far apart for meaningful contact. But the mathematics of slow, patient expansion does not require contact between distant stars. It requires only that each colony send out a new expedition when it is ready, at whatever pace the civilization chooses to sustain. Even a civilization that expands at the speed of a glacier in geological terms would have saturated the Milky Way many times over in the time available. The paradox does not need aliens to be close. It does not need them to be broadcasting. It does not even need them to be alive today. It only needs one of them, at any point in the last several billion years, to have survived long enough and been motivated enough to begin the slow process of spreading outward. And if even one did, we should know it by now. The absence of that knowledge is the paradox. The silence is not nothing. The silence is, in a very precise and deeply troubling sense, the loudest thing in the universe. All of this comes from a question asked between courses at a lunch table in the summer of 1950 by a man who was already famous for building the most dangerous machines in human history. Fermi would be dead in 4 years, taken by the same invisible radiation that had permeated the laboratory rooms where he had done his greatest work. He would not live to see the first satellite in orbit, or the first human in space, or the first systematic attempt to listen for signals from other stars. But the question he dropped into the conversation at the Fuller Lodge that day has outlasted him, and it has grown heavier with every passing year of silence that has followed it. Where is everybody? The question has not gotten easier. It has only gotten sharper. And the next chapter of this story begins with the people who decided that the only honest response to that question was to actually listen. Before any of this could become a paradox, before anyone could call it by that name or argue about its implications, it had to be confronted as a simple empirical fact. And that empirical fact was this: the galaxy has had 10 billion years to produce civilizations, and a civilization that begins to expand at even a glacially slow pace has more than enough time to reach every corner of the Milky Way before any of those 10 billion years run out. This is not a speculation or a theoretical hope, it is arithmetic. Think of it in human terms. Our species has been anatomically modern for roughly 300,000 years. We built the first genuine cities about 6,000 years ago. We developed radio technology about 130 years ago. We launched the first human-made object into space 76 years ago. From the emergence of Homo sapiens to the first satellite in orbit took roughly 300,000 years. In the scale of the Milky Way's 10 billion years, 300,000 years is less than the blink of an eye, less than 30 millionths of galactic history. The implication is that a civilization only needs a tiny head start on us to have already solved problems we have not yet begun to think about. A civilization that arose on a habitable planet 6 billion years ago, which is not only possible, but required by the fact that the galaxy has had 6 billion years of stellar evolution preceding our sun's formation, would have had so much more time than us that the comparison becomes almost meaningless. 6 billion years is 20,000 times longer than the entire span of human anatomical modernity. Whatever that civilization might have accomplished, built, and spread across the galaxy in that incomprehensible span of time staggers even the most expansive imagination. Yet, the sun moves through the outer arm of the Milky Way in a stellar neighborhood that shows no sign of ever having been visited, modified, or even noticed. Our solar system contains 4 rocky inner planets, 4 gas and ice giants, a belt of asteroids, a ring of distant icy objects, and 1 warm, wet, biosphere-covered world. None of those objects show any trace of construction, alteration, or contact by any intelligence other than the one that arose here. The solar system looks exactly as it would look if it had been developing in complete isolation since its formation 4.5 billion years ago, which is, of course, entirely possible. But if the galaxy contains thousands or millions or billions of civilizations that have had billions of years in which to expand and explore, the solar system's pristine, unmodified, untouched appearance becomes very difficult to explain. This is what the astronomer and science writer Timothy Ferris once described as the problem of the cosmic real estate. If intelligence is genuinely common and generally long-lived, then space is valuable real estate, and entities that survive long enough develop reasons to occupy it. Even if you reject the idea that any civilization would be expansionist in a military or colonizing sense, it is hard to imagine that every civilization across all of galactic history has consistently chosen to leave the vast, resource-rich void of interstellar space completely untouched. Stars represent enormous amounts of energy. Planets represent enormous amounts of raw material. Asteroids and moons and cometary nuclei represent accessible sources of metals, ices, organic compounds, and other useful things. A civilization that persists for millions or billions of years without exhausting or needing its home star system's resources would be unusual even by the standards of extraordinary restraint. And yet, our solar system shows no sign of ever having been visited, mined, harvested, or used in any way by any external intelligence. There is another dimension to the silence that goes beyond the absence of visitors. If any civilization in the history of the galaxy had developed broadcasting technology comparable to or more advanced than ours, radio telescopes, laser transmitters, any technology that puts electromagnetic radiation into space in a structured, non-natural pattern, and had operated that technology for any meaningful period of time, we might expect to detect the leakage. Our own civilization has been pumping radio signals into space since the early 20th century, and those signals are now more than 100 light-years from Earth, expanding outward in an ever-growing sphere that eventually reaches every star within that radius. The earliest television broadcasts, the radar pulses from the Second World War, the first deliberate radio transmissions to distant stars, all of it is out there, spreading at the speed of light, growing fainter with distance, but in principle detectable by a sufficiently sensitive instrument. Any civilization within 100 light-years of us that has a radio telescope pointed in our direction could, in principle, detect the fact that something technological is happening on this planet. Now, extend that logic across the galaxy. A civilization that has been broadcasting for 1,000,000 years would have bathed a sphere of roughly 1,000,000 light-years in its radio leakage, a volume that extends far beyond the Milky Way itself. Any civilization that has been detectable in this way for even a tiny fraction of the galaxy's history would have filled an enormous volume of space with the electromagnetic evidence of its existence. For that kind of signal to be completely absent from everything we have ever detected, either every civilization in the galaxy has been technologically quiet for its entire existence, or no civilization in the galaxy has been broadcasting at any frequency we can detect for any appreciable length of time, or the volume of the galaxy we have actually sampled is so tiny and our instruments so limited that we simply have not gotten lucky yet. That last possibility is real and important, and it provides one of the few genuinely cautionary notes in the whole discussion, despite 6 decades of searching. We have monitored only a tiny fraction of the possible target stars at a limited range of frequencies for a historically brief period of time. The parameter space of the search is vast, and we have explored only a corner of it. This does not resolve the paradox, but it does temper some of the sharper conclusions. The absence of a confirmed signal is not the same as confirmation of absence. These are different statements, and the second is far stronger than anything the evidence currently supports. Still, the argument from colonization timescales is not about signals. It is about physical presence, and there the silence is harder to explain away. The solar system has been accessible for 4.5 billion years. The evidence of any engineering at cosmic scales anywhere in the galaxy is, as of any survey we have conducted, 0. The evidence of any structured radio or optical signal from beyond Earth is, after 6 decades of searching, exactly one unconfirmed candidate that lasted 72 seconds and has never repeated. The evidence of any artifact from beyond the solar system passing through our vicinity is, despite the occasional interstellar visitor like Oumuamua, the elongated, tumbling, interstellar object detected in 2017 that generated enormous excitement and subsequent scientific controversy, entirely consistent with natural origins and inconsistent with artificial manufacture. The paradox is not solved by saying that we are in an early moment of the search, though that is true. It is not solved by saying that space is big, though that is also true. It is deepened by a fact that has only become more pronounced with time and with each new generation of instruments. The universe is not merely silent. It is silent in a way that cuts against every prediction one would make if the galaxy were genuinely populated with even a modest number of long-lived technological civilizations. The silence is systematic. It is total. And it began long before we started listening, because if the galaxy had been colonized at any point in the last billion years, the evidence would be all around us, encoded in the structure of the solar system itself, and we would not need a radio telescope to see it. We would need only to look up and notice that our world was not the isolated, untouched, apparently unremarkable blue planet that every observation we have ever made confirms it to be. Fermi asked the question once and then moved on to other things. The question did not move on. It has been circling the halls of physics and astronomy ever since, gathering weight with every passing year of silence, growing more urgent as our instruments improve and our search deepens, and the answer continues to be the same. Where is everybody? No one knows. And the longer no one knows, the more important the question becomes, not as a curiosity about alien biology or a puzzle for astronomers to solve on their lunch breaks, but as the most profound empirical mystery our species has ever confronted. The silence of the cosmos has something to tell us. We have been listening hard enough to know that. We just do not yet know what it is saying. That is the shape of what Fermi stumbled onto at the lunch table in the summer of 1950, in the weeks before the Korean War began and the decade before the first human left Earth. He was not the first to notice the silence. The 19th century French philosopher and writer Bernard Le Bovier de Fontenelle had gestured toward it as early as 1686, asking in his Conversations on the plurality of worlds why the inhabitants of other planets had not yet come to visit us. The Soviet rocket scientist Konstantin Tsiolkovsky had noted the same uncomfortable absence in a private manuscript written in 1933, remarking that the absence of visitors from other worlds was itself a kind of answer about the rarity of intelligent life. And Jules Verne had contemplated the enormous emptiness of space in ways that prefigured the question without quite asking it directly. But none of them had Fermi's particular gift for compression, for taking the sprawling, untidy enormity of a problem and reducing it to its sharpest possible point. The question, where is everybody, does what the best Fermi problems do. It treats something enormous and apparently unanswerable as a matter of arithmetic. It says, given everything we know, here is what we should expect to see. Given everything we observe, here is what we actually see. The gap between those two things is not a matter of taste or interpretation. It is a matter of logic, and it cannot be dismissed. The formal name for that gap, Fermi paradox, did not appear in the scientific literature until 1977, a quarter century after the question was first asked. In the years since, it has accumulated a body of proposed solutions that now numbers in the dozens and perhaps the hundreds, if you count all the variants and subvariants that researchers and theorists have put forward. Some of those solutions are comforting, some are deeply disturbing, some are both simultaneously, depending on which direction you look at them. Each one will be examined in the chapters of this story that follow. But before any of them can be properly evaluated, you have to understand what the search for the answer has actually looked like, not as an abstraction, but as a lived human activity carried out by real people with real instruments over real decades, producing a result that is real and specific and undeniable. The search produced silence, not absence of effort, silence as a result. And silence, in science, is always an answer, even when it is not the answer anyone wanted to hear. In the spring of 1960, a 29-year-old radio astronomer named Frank Drake pointed an 85-foot dish antenna at two nearby stars and began the first systematic attempt in human history to detect a signal from another civilization. The telescope sat at the National Radio Astronomy Observatory in Green Bank, West Virginia, a quiet valley chosen for its natural shielding from radio interference, where the surrounding mountains helped block out the noise of human civilization that might otherwise drown out anything the cosmos had to say. Drake had spent the better part of 2 years designing the project and convincing the observatory's director to give him time on the telescope for what he called Project Ozma, named after the Queen of El. Frank Baum's imaginary land of Oz, a place Baum had described as very far away, difficult to reach, and populated by strange and exotic beings. The two stars Drake chose were Tau Ceti and Epsilon Eridani, each located approximately 11 light-years from Earth. Both were sun-like stars, thought to be reasonable candidates for harboring planets capable of supporting life. Neither was actually known at the time to have planets. The first confirmed exoplanet discovery was still 35 years in the future. But the logic was sound enough. If you wanted to listen for a message from another civilization, you started with the stars, most like your own. Drake tuned the telescope to a frequency of approximately 1,420 megahertz, the frequency at which neutral hydrogen atoms naturally emit radio energy, a frequency that any civilization with a basic knowledge of physics would recognize as universal and unambiguous. This was the hydrogen line, the electromagnetic fingerprint of the most abundant element in the universe. And the thinking was that any civilization attempting to broadcast a signal across interstellar space would choose it deliberately as a kind of cosmic beacon that transcends any language barrier. For 6 hours a day, from April to July of 1960, Drake and his small team aimed the telescope at Tau Ceti and then Epsilon Eridani, scanning for any narrowband signal that stood out from the background noise, any pattern, any repetition, any structure that could not be explained by natural astrophysical processes. The team used a chart recorder and a loudspeaker to monitor incoming signals, listening in real time to whatever the telescope received. The loudspeaker produced the static hiss, that is the baseline sound of the universe, that continuous undifferentiated noise that constitutes the universe's background chatter, the overlapping voices of 1 billion natural radio sources blending into something that sounds, to a human ear, exactly like nothing. There was one false alarm early in the project, when the receiver picked up a strong, structured signal that briefly created a surge of excitement before being identified as aircraft radar. Then the speaker went back to its static, and the chart recorder went back to its flat wiggles. And Project Ozma continued for 4 months without returning a single signal that could not be explained by natural causes or human interference. When it ended, Drake was clear-eyed about what he had accomplished. The survey had been too short, the frequency coverage too narrow, and the 2 stars too few to draw any conclusions about the prevalence of intelligent life in the galaxy. But the result, nothing, was still a data point, and it was an honest one. The universe, in the direction of Tau Ceti and Epsilon Eridani, in the frequency range near the hydrogen line in the spring and summer of 1960, had nothing to say to us. The interest generated by Project Ozma was considerable enough that the following year, Drake was asked to organize a small scientific conference at the same Green Bank facility to discuss the prospects of the search more broadly. About a dozen researchers attended, an eclectic group that included physicists, astronomers, biologists, and engineers. To give the discussions some structure, Drake wrote down a simple equation on a blackboard, a framework for estimating the number of civilizations in the Milky Way that might currently be broadcasting signals we could detect. The equation was not designed to give a precise answer. Drake himself said it was more like an agenda than a calculation, a way of organizing what was known and what was unknown, and of identifying where the key uncertainties lay. But it became one of the most famous equations in the history of science, carrying his name ever since. The Drake equation multiplied together a series of factors: the rate at which new stars form in the Milky Way, the fraction of those stars that have planetary systems, the average number of planets per system capable in principle of supporting life, the fraction of those planets on which life actually develops, the fraction of life-bearing worlds on which intelligence emerges, the fraction of intelligent civilizations that develop detectable technology, and finally the most uncertain and the most haunting factor of all, the average length of time for which a communicating civilization remains detectable before it falls silent. Multiply those 7 numbers together and you get an estimate, however rough, of the number of civilizations in the galaxy that are sending out signals right now that we could, in principle, pick up if we pointed the right instrument in the right direction. When Drake ran through the equation at the 1961 conference, using the best estimates available at the time, his answer was somewhere between 1,000 and 100 million communicating civilizations in the Milky Way. The first 5 factors in the equation, the astronomical and biological ones, seemed, even in 1961, likely to be reasonably favorable. Stars formed at a steady rate. Planets appeared to be common. Life had arisen quickly on Earth within the first billion years of the planet's existence, if the fossil record could be trusted. Intelligence had arisen, eventually, though the path from single-celled organisms to something capable of building radio telescopes had taken 3.5 billion years. The optimistic interpretation of these facts was that the galaxy should be full of civilizations at various stages of development. The pessimistic interpretation, or rather, the sobering one, was that the final factor, the lifetime of a civilization, could pull the whole product down to almost nothing. If civilizations typically destroy themselves within a few centuries of achieving technological capability through war, environmental collapse, or some other catastrophe that the equation does not specify, then even a galaxy brimming with inhabited worlds might contain very few civilizations that are currently broadcasting signals. The Drake equation reveals something about why the Fermi paradox cannot be solved simply by assuming life is common. Life being common is not enough. What matters is whether intelligent, communicating civilizations persist long enough to be detectable and whether the answer to that question is shaped by forces internal to civilizations themselves rather than by the difficulty of evolution. This is where the search for extraterrestrial intelligence becomes something more than an exercise in astronomical probability. It becomes a question about the nature of civilizations, about whether the developmental trajectory from simple chemistry to technological complexity consistently leads to survival or consistently leads to self-destruction, about whether intelligence, once it arises, tends to persist or tends to burn itself out. Drake's equation does not answer that question. It only makes clear that the answer to that question is the most important variable in the entire calculation. The search that followed Project Ozma spanned more than 6 decades. The methods expanded dramatically. Radio surveys gave way to broadband scanning systems capable of monitoring millions of frequencies simultaneously. Optical SETI programs searched for brief, powerful laser pulses that a transmitting civilization might send across the light years. Surveys scanned the sky for the infrared waste heat that would be generated by enormous energy-harvesting megastructures. Theoretical constructs called Dyson spheres, named after physicist Freeman Dyson, who proposed in 1960 that a sufficiently advanced civilization might eventually dismantle its home star's planetary system and use the material to build a vast shell around the star, capturing essentially all of its energy output. No such structure has ever been detected. The sky remains dark in the infrared frequencies, where such a structure would most clearly advertise its presence. The Allen Telescope Array in California, a collection of 42 dish antennae that can monitor a wide swath of the sky continuously, has run searches covering thousands of target stars. The massive FAST telescope in Guizhou province in China, the world's largest single-dish radio telescope, 500 meters across, with a collecting area roughly 30 times greater than the famous Arecibo instrument that it surpassed, has pointed its enormous ear at dozens of potentially interesting targets, including the TRAPPIST-1 system, the nearby planetary system that has attracted so much attention since its full complement of 7 Earth-sized planets was discovered and characterized. In 2025, a dedicated SETI scan of the TRAPPIST-1 system using FAST searched the frequency range from approximately 1050 MHz to 1450 MHz for more than an hour. The system contains 3 planets in the habitable zone of their star, at a distance of only 40 light-years from Earth. It is one of the most tempting targets in all of SETI research. The search detected no signals of extraterrestrial technological origin. The combined total of 6 decades of searching, which encompasses thousands of individual observation sessions, dozens of distinct research programs, multiple generations of increasingly sensitive instruments, and the analysis of data contributed by millions of ordinary computer users through the Volunteer Distributed Computing Project, known as SETI at Home, has returned a catalogue of unexplained signals that numbers fewer than the fingers on one hand. None of them has ever repeated. None of them has been confirmed. None of them has been demonstrated to be artificial in origin. The silence from the cosmos has not been for want of listening. The silence has been total, systematic, and undeniable. And then there is the one signal that almost broke the silence, the one moment in all of those decades when the instruments returned something that looked, for a breathtaking instant, like exactly what everyone had been waiting for. On the night of August the 15th, 1977, the Big Ear radio telescope at Ohio State University a fixed-position radio antenna, spread across a field in Delaware, Ohio, roughly the size of 3 football fields placed end to end, was doing what it always did, scanning the sky as the Earth rotated, recording the radio emissions from whatever portion of the heavens happened to drift through its beam. The telescope had been repurposed to SETI work in 1973, becoming what would eventually be the longest-running dedicated SETI program in history, ultimately continuing until the observatory was demolished in 1997 to make way for a golf course expansion. On that August night, something happened. A signal rose in the recording channel that monitored the frequency closest to the hydrogen line, 1420.4 MHz, just barely above the natural emission frequency of neutral hydrogen. The signal did not drift. It did not spread across a range of frequencies in the way that natural broadband sources do. It was narrowband, concentrated, distinct. It rose and fell precisely as a fixed-point source in the sky would rise and fall as the telescope's beam swept past it during Earth's rotation, exactly the profile predicted by the telescope's geometry for a genuine astronomical source. The whole event lasted 72 seconds, and then it was over. 3 days later, a volunteer astronomer named Jerry Amon sat down with a stack of paper printouts, recording Big Ear's observations. The telescope's data was encoded in alphanumeric characters representing signal intensity, with higher intensity detections, producing letters rather than numbers, a coding scheme where ordinary background noise produced ones and twos, while anything extraordinary would produce letters further into the alphabet. Eamon was scanning the printouts for anything unusual when he found a sequence that read 6 E Q U J 5. In the coding system, the letter U represented a signal approximately 30 times as intense as the background. No previous Big Ear observation had ever produced anything remotely like it. Eamon grabbed a red pen, circled the sequence, and wrote a single word in the margin of the printout: wow. The wow signal, as it has been known ever since, bore every characteristic that SETI researchers had long predicted a genuine extraterrestrial transmission might possess. It occurred at the hydrogen line frequency. It was narrowband. It rose and fell with the exact profile of a fixed celestial source. It was 30 times as strong as the background noise. And it came from the direction of the constellation Sagittarius, which lies roughly toward the central bulge of the Milky Way, a direction dense with stars. If you had set out in 1959 to describe what an artificial extraterrestrial signal would look like when one was finally detected, you would have described something very much like what Jerry Amon found, circled in red ink on that printout. And then it was gone. Follow-up observations at the same point in the sky, using the same telescope, began within days and continued for years. The Very Large Array, a system of 27 radio telescopes in New Mexico that is far more sensitive than Big Ear, searched the region of sky associated with the signal. The Arecibo Observatory, which at the time of its operation boasted the largest single-dish radio telescope in the world, searched the same coordinates. Dozens of independent searches scanned the same sky position over the following 4 decades, with instruments that improved in sensitivity with each passing year. Not one of them ever detected the signal again. Not once. Not a whisper. The wow signal appeared exactly once in a single 72-second observation window, and then vanished from the universe as completely as if it had never existed. The mystery persisted for 47 years. Various candidate explanations were proposed and evaluated, including reflections of satellite transmissions, aircraft radar leaking into the protected radio astronomy frequency band, and fleeting natural astrophysical events. None of them survived rigorous scrutiny. In 2017, a researcher proposed that the signal might have been produced by the hydrogen-rich cloud of gas and ice surrounding a comet that was passing through the telescope's field of view at the time. This explanation attracted attention for several years, but was disputed by Jerry Ehman himself and other researchers who pointed out that the signal's properties were not consistent with what you would expect from a cometary hydrogen cloud. Then, in a 2024 preprint study led by Abel Mendez of the University of Puerto Rico, the research team examined archival data from the now demolished Arecibo Observatory and found a small number of weak, narrowband signals near the hydrogen line frequency. Analyzing the properties of these signals alongside a re-examination of the original Big Ear archival data, the team proposed a candidate natural explanation for the WOW signal. The event may have been produced by a rare hydrogen line flare from a small, cold cloud of neutral interstellar hydrogen that was briefly energized by an intense pulse of external radiation, possibly from a magnetar, a class of neutron star that occasionally erupts in gamma-ray and X-ray flares of extraordinary power. Under this hypothesis, the signal would still be extraordinary. It would be a rare and unusual astrophysical event, but it would not be artificial. It would not be an intelligence reaching out across the light years. This hypothesis is, as of June of 2026, a candidate explanation. It has not been confirmed. The 2025 paper by the same research team that revisited the Ohio SETI archival data in more detail revised some of the WOW signal's properties, estimating a peak flux density above 250 Janskis and a frequency of approximately 1420.726 MHz, which places it slightly above the standard hydrogen line. The team's analysis is careful, and the proposed natural mechanism is plausible, but the origin of the WOW signal remains officially unresolved. No one can say with certainty today where it came from. The honest answer, and the only scientifically defensible answer, is that we do not know. What we do know is what the WOW signal represents within the broader context of the search. It represents the closest that 6 decades of systematic listening has ever brought us to a signal that looked like what we were looking for. It came once, lasted 72 seconds, and was never heard again. In every year since 1977, in every observation session, in every new survey, with every instrument more sensitive than the last, that signal has been the high water mark. Nothing else has come close to it. And even that, most tantalizing of hints, may turn out to have a perfectly natural explanation that has nothing to do with intelligence. The James Webb Space Telescope, the most powerful space observatory ever launched, which began scientific operations in 2022 and has since reshaped our understanding of galaxy formation, star birth, and planetary atmospheres, has now begun characterizing the atmospheres of rocky, Earth-sized planets in the habitable zones of nearby stars. The TRAPPIST-1 system is the primary target. Its 7 Earth-sized planets are close enough to their star to receive measurable infrared signal through the telescope's spectrographic instruments, and 3 of them orbit in the zone where liquid water could exist on a rocky surface. As of June of 2026, the James Webb Space Telescope has examined the atmospheres of multiple TRAPPIST-1 planets. It has found no evidence of thick, hydrogen-dominated primary atmospheres on the inner planets, a result consistent with these worlds having denser, secondary atmospheres, more like the rocky planets of our own solar system. But it has detected no confirmed biosignatures, no anomalous oxygen, no excess methane, no nitrogen dioxide signatures that would hint at biological processes at work, no atmospheric fingerprints of life. This is not a failure of the telescope. The James Webb Space Telescope is doing exactly what it was designed to do, and it is doing it with extraordinary precision. The fact that it has not yet found a biosignature is important information about those specific planets, and the search is far from exhausted. Many more observations of TRAPPIST-1 and other target systems are planned. But it is worth noting the broader context. The nearest confirmed habitable zone planetary system to Earth, a system containing 3 planets in the zone where life might conceivably arise, at just 40 light-years away, has so far returned no signal of biology detectable from a distance. The universe, even up close, remains quiet. 6 decades of active, methodical, progressively more sensitive searching have produced this. One unexplained 72-second detection from August of 1977 that may or may not have been artificial, and which has never repeated, and which is now explained by some researchers as a rare natural event. Alongside it, the James Webb Space Telescope is scanning nearby planetary atmospheres for the chemical traces of life and finding none so far. And behind those specific results lies the broader shape of the silence, a silence that is not passive, not merely the absence of looking, but the active result of the most sophisticated listening project in the history of our species returning, year after year, nothing but the background hiss of a cosmos that, from our position in this galaxy, appears to have no one else in it at all. This is the scale of what the silence actually means. Not that we have looked everywhere and found nothing, because we have not looked everywhere. We have covered a vanishingly small fraction of the galaxy's stars, a narrow slice of the possible frequency range, a brief historical moment in the arc of cosmic time. But we have looked with the best instruments we know how to build, at the most promising targets we can identify, for long enough that the silence has accumulated into something that demands explanation. The silence is not ignorance. The silence is a fact. And the fact calls out for an answer that 76 years of serious thought, since Fermi asked his question at a lunch table in New Mexico, has not yet been able to supply. What is killing the stars before they can speak? Or is the answer something even stranger, that the stars have never had anything to say? That question is where this story goes next. The scale of the listening effort matters here, because one of the most persistent responses to the Fermi paradox is the argument that we simply have not searched long enough or widely enough to draw any conclusions. This argument has merit, and it should be stated clearly before examining where it falls short. Our SETI searches have covered a small fraction of the Milky Way's stars, a few thousand targets, out of a galaxy containing up to 400 billion. We have monitored a limited slice of the radio spectrum, even though the possible range of frequencies that an extraterrestrial civilization might use for communication is enormous. We have been searching for only 66 years, which is barely a rounding error on the scale of cosmic time. On all of these grounds, the argument that absence of evidence is not evidence of absence has genuine scientific standing, And anyone who claims that the silence definitively proves we are alone has made a logical error that the evidence does not support. But the colonization argument, introduced in Part 1, operates by a different logic than the signal search, and it is not saved by the same caveats. The question of whether any civilization has ever colonized the galaxy is not answered by pointing a radio telescope at a few thousand stars for 66 years. It is answered by examining our own solar system, which has been physically accessible to any spacefaring civilization for 4.5 billion years, and determining whether any such civilization has ever modified it, visited it, left anything in it, or used it in any way. That examination has been conducted with increasingly powerful instruments for decades, and the answer, across every category of evidence, is negative. The solar system is pristine. Its structure is consistent with 4.5 billion years of natural, geological, gravitational, and chemical evolution. There are no anomalies that require artificial explanation. There is nothing here that should not be here, and nothing missing that should be here. The verdict of the solar system is not that we have not looked long enough. The verdict of the solar system is that no one has ever come. The tension between these two arguments, the legitimate humility about our limited search versus the harder-edged conclusion from the colonization timescale, is what gives the Fermi paradox its staying power and its genuine intellectual bite. It cannot be dismissed as a failure of imagination, because the imagination required to explain the silence is already operating at full stretch in every proposed solution. It cannot be dismissed as a failure of technology, because the physical evidence of colonization would not require radio telescopes to detect it, would be written into the structure of our own solar system, in the same way that the chemical and geological history of Earth is written into its rocks and oceans and atmosphere. And it cannot be dismissed as culturally biased wishful thinking, because the mathematics of colonization timescales do not care whether we want aliens to exist or not. They care only about distances, speeds, and time. And the math says that the galaxy is old enough and the distances are traversable enough for any civilization that survived and wished to expand to have done so many times over by now. This is why the scientific response to the paradox has, over the 6 decades since Project Ozma, split into 2 broad camps, each of which is internally coherent, but which leads to conclusions that are difficult to hold comfortably. The first camp argues that intelligent life is rare extraordinarily, almost impossibly rare, and that we exist in conditions so specific and so unlikely that the emergence of a civilization like ours may have happened only once or only a handful of times in the entire observable universe. This camp encompasses what is known as the rare Earth hypothesis, the idea that Earth's particular combination of properties, its location in the Milky Way, its distance from its star, the presence of a large stabilizing moon, the existence of plate tectonics to recycle carbon and regulate temperature, the protective magnetic field generated by its iron core may be so extraordinary that habitable worlds capable of producing complex life are vanishingly uncommon. On this view, the silence is simply explained. There is almost no one out there to make any noise. The second camp takes the opposite position on the prevalence of life, but then must grapple with the even darker question of what eliminates civilizations before they can be detected. If life is common, and if intelligent life arises with any regularity on inhabited worlds, then the silence demands a different explanation, not rarity of origin, but failure of persistence. Something must be stopping civilizations from surviving long enough to spread across the galaxy and fill it with detectable signals and physical artifacts. What that something might be is a question that has attracted the attention of some of the most rigorous thinkers in science and philosophy over the past several decades. And the answer that emerges from that inquiry is one of the most unsettling ideas in all of modern scientific thought. It does not stop at explaining the cosmic silence. It extends all the way into our own future, and it carries with it a warning. That warning is not delivered in this chapter. The evidence that leads to it, and the specific form it takes, belongs to the next stage of this story, where the proposed solutions are examined in full and the darkest possibilities are confronted honestly. But the stage is now set. We know what the silence is. We know how long and how carefully we have listened. We know that the silence is not for want of effort. We know that the one signal that came close to breaking at 72 seconds on a warm August night in 1977 has never returned, and may have a natural explanation that removes it from the category of evidence altogether. We know that the most powerful space telescope ever built is staring at the atmospheres of the nearest potentially habitable worlds and finding no sign of biology. We know that the mathematical argument for a galaxy saturated with civilizations is sound, and that the solar system's pristine condition gives no comfort to anyone who hoped to find a way around it. And we know that the question Fermi asked over lunch in 1950 has now had 76 years to be answered, and the answer that comes back every time and from every direction is still silence. What that silence means is the question that must now be confronted directly, with all of its implications intact, and with no comfortable exits left unexamined. 6 decades and 66 years of listening. That is the scope of what has been attempted. Not passive waiting, not casual glancing at the sky, but the dedicated work of scientists who built instruments, designed surveys, wrote software, analyzed data, and committed careers to a question they knew might never be answered in their lifetimes. Drake's 85-foot antenna in 1960 has been followed by progressively larger, more sensitive, more sophisticated instruments. The observational methods have evolved from single-frequency scanning to broadband digital analysis that can simultaneously monitor millions of frequency channels. The computational power devoted to the search has grown from single IBM mainframes, processing punch cards, to distributed networks of millions of personal computers, crunching exabytes of raw telescope data. The target list has expanded from 2 stars to thousands, and the theoretical framework for what to look for has expanded from narrowband radio signals to laser pulses, to infrared signatures of megastructures, to atmospheric biosignatures on nearby worlds. Every improvement in capability has returned the same answer. The universe, as far as our instruments can tell, has nothing to say to us. That silence, accumulated across 6 decades of deliberate effort, is not a gap in the data. It is the data. In 1996, an economist named Robin Hanson wrote an essay that reframed the Fermi paradox in a way that has never been fully escaped. Hanson was not an astronomer. He was not a physicist. He was a researcher whose training spanned economics, statistics, and the philosophy of science. And he approached the silence of the cosmos the way an economist approaches any market anomaly, by asking what the absence of the expected product implies about the conditions of supply. What he concluded, and what he published under the title "The Great Filter: Are we almost past it? Was not a specific answer to the Fermi paradox. It was something more disturbing. It was a logical framework that converts every possible answer to the paradox into a statement about humanity's own future and ensures that no answer is cheap. Every explanation you might offer for why the sky is silent carries a price, and some of those prices, depending on what we discover in the coming decades, could be catastrophic. The framework begins with a simple observation that Hansen formalized with unusual precision. The universe has produced at least one intelligent, tool-using, technologically capable civilization, us. It has not, as far as we can determine with any of the instruments we have built or any survey we have ever conducted, produced another one that has been detectable in any of the ways we know how to look. Given the age and scale of the galaxy, and given the mathematics of expansion that were laid out in the earliest part of this story, this fact implies that somewhere between the initial formation of rocky planets and the emergence of civilizations like ours, there is at least one step, possibly several, that is so profoundly improbable that it filters out almost everything that attempts to cross it. Hansen called this bottleneck the Great Filter. It is not a physical object. It is a statistical necessity. If the galaxy is old, and life should be easy to produce, and intelligence should follow naturally from life, and technology should follow from intelligence, then the galaxy should be full of civilizations. It is not. Therefore, the pathway from bare chemistry to cosmic civilization contains at least one step that almost nothing survives. That step, wherever it is the Great Filter. Now here is the question on which everything turns. Where in the sequence is the filter located? Is it behind us or ahead of us? Has humanity already crossed the most improbable step, surviving against extraordinary odds to reach the technological stage we now occupy? Or does the bottleneck lie somewhere in our future, waiting for every civilization that reaches our current level of development, eliminating each one before it can spread across the stars? These two possibilities are not symmetrical. They are not equally comfortable to contemplate. If the filter is behind us, then we are extraordinarily rare, perhaps unique, or nearly so, in the observable universe. But our future is potentially open. The silence all around us reflects our rarity at having already cleared the hardest hurdle. We are the ones who made it through. If the filter is ahead of us, the situation reverses entirely. The filter's presence in our future means that civilizations do reach our level of development with reasonable regularity. Life arises, intelligence develops, technology follows, and then something eliminates them, all of them or nearly all, before they can spread, and that something is waiting for us as well. In this second scenario, our existence is not evidence of extraordinary luck. It is evidence that we have not yet reached the step where civilizations die. Robin Hansen was careful and precise about why this distinction matters so profoundly. The key logic runs as follows. The likelihood that the filter is behind us is inversely related to how easy the steps before us have been. The more we discover that life emerges readily on rocky planets in habitable zones, the more we discover that complex multicellular organisms are a natural consequence of evolution given enough time. The more we discover that intelligence arises frequently in biologically complex worlds, the worse our situation becomes. Because if all of those steps are easy, then many civilizations should have reached our level, and many of them should have gone on to colonize the galaxy, and they have not, which means the filter must be somewhere beyond where we currently stand. The better the news about life's ubiquity, the worse the news about our future. This is the sharpest and most counterintuitive edge of the Great Filter hypothesis, and it is the one that Oxford philosopher Nick Bostrom articulated most clearly in an essay he published in 2008 under the deliberately provocative title, "Where Are They? Why? I Hope the Search for Extraterrestrial Life Finds Nothing." Bostrom argued that the discovery of any life beyond Earth, particularly any life that arose independently, in a separate lineage, on a separate world, would shift the probability distribution for the filter's location in a deeply concerning direction. He was not worried about advanced communicating civilizations. He was worried about pond scum. He was worried about fossil bacteria in Martian rock. If NASA's robotic missions were to return a sample from Mars containing the chemical signature of past biology, that discovery would tell us something that sounds wonderful but carries a hidden weight. Life is not rare. Given that life arose on two planets in the same solar system, the probability that it arises readily across the galaxy becomes much higher, which means, by the logic of the Great Filter, that the filter cannot be at the origin of life's step, because life makes it past that step routinely, which pushes the filter forward, which pushes it closer to us. Bostrom put it plainly: the more complex the life found elsewhere, the worse the news becomes. Simple extinct microbes would be bad news. Fossil trilobites would be very bad news. The skeleton of anything that resembled a small mammal would be, in his words, the worst news ever printed on the front page of a newspaper, because a mammal-like creature would imply that evolutionary complexity, the production of animals with nervous systems, with something approaching behavior, with brains, is not rare either, which would push the filter even further forward, past all the biological stages, into the cultural and technological stages, closer to us and to our immediate future. This is not a comfortable framework to live with, but it is a logically coherent one, and it structures the rest of the proposed solutions to the Fermi paradox in a way that strips away a great deal of their surface comfort. Every proposed answer to "why is the sky silent" must be mapped onto the question of where the filter is, and no answer comes without a cost. Take the rare Earth hypothesis, which was formalized in 2000 by paleontologist Peter Ward and astronomer Donald Brownlee of the University of Washington in their book of the same name. Ward and Brownlee argued that complex life, not microbial life, which they believed was probably widespread, but the kind of multicellular, nervous system possessing, intelligent life that can build radio telescopes, requires an exceptional combination of circumstances, so numerous and so specific that its emergence may be extraordinarily rare throughout the universe. The list they assembled is formidable. A galaxy of the right size and age and metal content so that the heavy elements needed for rocky planet formation are abundant. A position within that galaxy far enough from the dangerous, radiation-intense central regions to avoid sterilizing bursts of energy from supernovae and gamma-ray sources, but not so far toward the outer edge that the chemistry of planet formation is too impoverished. A star of the right type, not a red dwarf, which might tidally lock its planets and shower them with flares, and not a massive blue star, which burns out too quickly for life to have time to develop, but a stable yellow or orange sun-like star with a lifespan measured in billions of years. A planet at the right orbital distance for liquid water. A large moon like ours, massive and gravitationally stabilizing, keeping the planet's axial tilt within a range that produces manageable seasonal cycles rather than catastrophic swings. a Jupiter-sized gas giant in an outer orbit whose gravitational influence deflects or absorbs the worst of the incoming cometary and asteroidal traffic that would otherwise pummel the inner system at catastrophic rates. Plate tectonics, driven by radioactive heat in the planetary interior, cycling carbon through the lithosphere and regulating atmospheric temperature over geological time. A strong magnetic field generated by a molten iron core, shielding the surface from the most destructive forms of cosmic radiation. Ward and Brownlee multiplied the probabilities of all these factors together and arrived at a deeply unsettling estimate. The number of planets in the Milky Way capable of hosting the kind of complex life that produces intelligence and technology may be measured not in the billions, but in the very low thousands, or perhaps in the tens, or perhaps in single digits, or perhaps, if some of the probability estimates are correct, in something less than one. Perhaps Earth is the only such place in the galaxy. Perhaps we are truly alone, not because intelligence was eliminated, but because it never had a chance to arise anywhere else in any form that would be recognizable to us. The rare Earth hypothesis places the filter in the distant biological past, in the improbable accumulation of physical and chemical and planetary conditions that allowed complexity to arise here. On this view, the galaxy is not littered with extinct civilizations that failed to cross a barrier ahead of us. The galaxy is simply nearly empty to begin with, a vast, dark volume in which the conditions for our kind of life are so unusual that we represent a fluke of extraordinary improbability. This is a filter behind us interpretation. It is the most optimistic form of the paradox's resolution, in the sense that it implies we are rare but not doomed. But it is also its own form of isolation, a cosmic solitude so profound that no one has ever existed to see us, and in all probability no one ever will. The rare Earth hypothesis has critics. Many researchers argue that Ward and Brownlee underestimated the adaptability of life, the range of environments in which it could arise, and the possibility that the specific conditions they listed as necessary may each have alternatives that work equally well. Life might arise around red dwarf stars in ways that Earth life's evolutionary history does not capture. Plate tectonics might not be strictly required for geochemical cycling if other mechanisms serve the same function. The large moon might stabilize axial tilt less than assumed, or planets might find other paths to climate stability. The discovery of extremophiles organisms that thrive in conditions once considered lethal, including scalding hydrothermal vents, highly acidic lakes, frozen Antarctic rock, and the intensely radiation-exposed interiors of nuclear reactors, has expanded the known envelope of conditions compatible with life and made the biologist's notion of habitable increasingly difficult to define narrowly. But the rare Earth debate, however it resolves, does not eliminate the filter. It only relocates it. Even the most optimistic reading of Earth's biological and planetary history requires some explanation for why the galaxy is not visibly colonized. Even if life is common, even if complex life is common, even if intelligence is common, the silence demands an answer. And when you set the rare Earth hypothesis aside and try the more troubling alternative, that life is genuinely widespread and intelligence is not rare, you are forced to confront the second family of proposed solutions, the ones that place the filter not in the past, but in the future. And these are the solutions that require the most nerve to look at directly. The category of self-destruction filters encompasses a grim zoo of possibilities. a civilization that develops nuclear weapons and then fails to manage the political conditions under which they might be used. A civilization that alters its atmosphere faster than it can adapt, collapsing the ecological conditions that support its population. A civilization that engineers biology pathogens, modified organisms, genetic technologies, with a precision that outstrips any governance structure capable of preventing misuse. A civilization that builds artificial intelligence systems of sufficient capability that those systems pursue goals misaligned with the civilization's survival. A civilization that exhausts its home planet's resources before achieving the technological independence of space colonization and then collapses back to subsistence before it can recover. What makes these proposed filters so disturbing is not any one of them in particular. It is the logic that underlies all of them as a class. Any of these scenarios, in order to function as a great filter, must be nearly universal. It must be a barrier that almost every civilization encounters and almost every civilization fails to cross. Because if even a small fraction of civilizations found a way to navigate nuclear weapons safely, or managed their ecological situation, or aligned their artificial intelligence, or colonized other worlds before their home planet's resources ran out, those successful few would still be here. Their descendants would have had billions of years to spread. Their artifacts would be all around us. The filter, to do the work the paradox requires it to do, must be something that eliminates essentially everyone, not most, essentially all. The self-destruction scenarios are terrifying not because they might happen to us, but because the silence of the galaxy suggests they must happen to nearly everyone who reaches our stage. The silence is not an accident. If these explanations are right, it is a pattern. The dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin in his 2008 novel of the same name. The second volume in the series that begins with the three-body problem offers a different kind of filter, one located not inside civilizations but between them. Liu's framework rests on two axioms that he argues are universal: that all life strives to survive and expand, and that the resources available in the universe are finite. From these premises follows a logic of predation. Every civilization that becomes aware of another civilization cannot be certain of that other civilization's intentions. It cannot be certain that the other is not hostile. And it cannot be certain that even a presently peaceful civilization will not become hostile as it grows and its resource needs intensify. Given the exponential pace of technological development, which Liu illustrates with the observation that a civilization a few thousand years more advanced than ours might be as far beyond us in capability as we are beyond Stone Age humanity, the only rational response to the detection of another civilization is to destroy it before it can become a threat. Not because all civilizations are aggressive, but because no civilization can afford to assume that the one it has discovered is not. The universe, under this model, is a dark forest. Every civilization is an armed hunter moving in silence through the trees. The moment you reveal your position to another hunter, you become a target. The survival strategy that works in a dark forest is to make no noise. The dark forest hypothesis has the advantage of explaining the silence without requiring either the rarity of life or the universality of self-destruction. All the civilizations are still there. They have simply learned, through bitter experience or careful reasoning, that the optimal strategy is perfect silence. We, by broadcasting our presence with decades of radio and television transmissions, spreading outward in a sphere that now encompasses many nearby star systems, may have already violated that silence in ways we cannot take back. On this view, the absence of any signal reaching us is not evidence that no one exists. It is evidence that everyone who exists has understood why sending a signal is suicidal. And we are the exception. The young civilization that has not yet learned the lesson, still shouting into a forest full of armed hunters. Most astrophysicists who work on the Fermi paradox regard the dark forest hypothesis as the least probable of the major candidate explanations, precisely because it depends on a specific sociology that it presumes must be universal. For predatory silence to produce the total absence of observable signals, every civilization in the galaxy must have independently arrived at the same conclusion that broadcasting is lethal, and every one of them must have ceased all transmissions that might be detectable from a distance. That coordination of behavior, arising independently in civilizations separated by thousands of light years and evolving in completely different biological and cultural contexts, seems to require a kind of convergence that is very difficult to justify. And it is also not clear that perfect silence is achievable. A civilization that builds the equivalent of our industrial infrastructure generates waste heat in infrared frequencies, regardless of whether it tries to broadcast. A civilization that mines asteroids or constructs large artificial structures generates gravitational and optical signatures that even our current generation of telescopes could in principle detect. The dark forest would need to be populated by civilizations so advanced and so deliberately stealthy that no trace of their existence leaks into any frequency band we can monitor, and that seems, on reflection, to require more rather than less coordination among civilizations that, by hypothesis, refuse to communicate with each other. The zoo hypothesis offers yet a different explanation. Advanced civilizations exist, are aware of us, and have chosen not to contact us in order to allow our natural development to proceed without interference. This is the cosmological equivalent of a nature reserve managed by an invisible conservancy. We are the subjects of observation, protected from contact with the wider galactic community by a consensus among more advanced species not to intervene. It is a pleasant image. It is also extremely difficult to evaluate scientifically, because any hypothesis that explains the silence by positing active, coordinated concealment by advanced agents can explain any possible observation. If they are hiding perfectly and have the technological means to do so, no evidence of their existence would reach us, and the absence of evidence cannot be used to test the hypothesis in the normal way. The zoo hypothesis may or may not be true, but it is not falsifiable in any straightforward sense, which places it outside the range of scientific tools and leaves it as a logical possibility rather than a scientific candidate. The transcension hypothesis, proposed by futures researcher John Smart, takes a different angle entirely. It suggests that civilizations do not expand outward into space because sufficiently advanced intelligence consistently turns inward toward miniaturization, virtualization, and the exploitation of increasingly dense information processing substrates, ultimately converging on a kind of inner space rather than outer space. On this view, advanced civilizations do not colonize galaxies, because colonizing a galaxy is a profligate use of resources compared to the far richer information environments achievable within a small volume of highly organized matter. They do not broadcast because they have moved beyond any technology we would recognize into modes of existence that do not generate detectable signatures in radio or optical or infrared frequencies. They transcend, in a literal sense, the scales at which we are looking. This hypothesis is intriguing and has a certain internal consistency, but it too faces the challenge that it must hold for essentially every advanced civilization, without exception, or the exceptions would have colonized the galaxy long ago. Each of these proposed solutions, rare earth, self-destruction, dark forest, zoo, transcension, and the many variants and combinations thereof, shares a structural feature that becomes clearer the more carefully you examine them. None of them is comfortable. Each requires either that we are extraordinarily rare and alone, or that something deeply troubling happens to essentially every civilization that reaches our level of development. The rare and alone answer is its own form of enormity. The something troubling answer requires that the something troubling is both common and nearly universal. There is no proposed solution to the Fermi paradox that says life is common, intelligence is common, civilizations are long-lived, and everything is fine, we just haven't bumped into anyone yet. The mathematics of colonization timescales eliminates that comfortable middle ground. The galaxy has been old enough for long enough that fine and common and long-lived should have produced a galaxy visibly full of civilizations by now. It has not. So either common is false, or long-lived is false, or both. And whichever turns out to be true, the implications reach us. The silence is not just data about aliens. It is data about us, about what we are, and about what may be approaching. And that is the territory that the final part of this story enters directly and does not leave easily. The eukaryotic cell provides one of the most compelling candidate locations for a behind-us great filter. The transition from simple prokaryotic cells, the kind that dominated Earth for its first 2 billion years, and still dominated today, in terms of sheer number and metabolic diversity, to the far more complex eukaryotic cell, is one of the strangest and most improbable events in the history of life on this planet. A eukaryotic cell contains a nucleus wrapped in its own membrane, a suite of specialized internal compartments, and organelles, including mitochondria, that are themselves thought to be the descendants of ancient bacteria that were engulfed rather than digested. The endosymbiotic merger that produced the mitochondrion, the energy-generating powerhouse of the eukaryotic cell, seems to have happened exactly once in Earth's history. Every plant, animal, fungus, and complex, single-celled organism on this planet is descended from a single event, that one ancient merger between two very different kinds of prokaryote. It happened roughly 2 billion years ago on a planet that already had nearly 2 billion years of microbial history behind it, and it may have been extraordinarily unlikely even given that much time. If the emergence of the eukaryotic cell is rare, genuinely, combinatorially rare, the kind of event that requires a specific set of chemical conditions and a specific set of microbial community relationships and a specific set of physical circumstances to converge in the right order, then the filter may lie at that juncture. Complex life, multicellular organisms, nervous systems, animal behavior, intelligence, technology, all of these follow from eukaryotic cells, and all of them would be eliminated at a stroke if the eukaryotic merger simply failed to happen on a given world. A planet might have a rich and thriving biosphere of bacteria and archaea for billions of years, cycling through the geochemical processes that keep a planet's atmosphere and oceans in chemical balance, and yet never produce anything more complex than a microbial mat. The planet would be alive. It would not be capable of intelligence. And because we are always guaranteed to find ourselves on the rare planet where the merger happened, since that is the only kind of planet on which we could exist, we cannot use the fact of our own existence to estimate how common the merger is. We need to look elsewhere. We need to find out how many planets have life, and then how many of those have complex life, and we do not yet know. The abiogenesis problem, the origin of life from non-living chemistry, is another candidate that several researchers have identified as potentially filter grade in its difficulty. Life on Earth appears to have arisen remarkably quickly after conditions became suitable. Fossil evidence suggests microbial life was present at least 3.5 billion years ago, possibly earlier, on a planet that formed 4.5 billion years ago and spent its first several hundred million years being bombarded by impacts intense enough to repeatedly vaporize any ocean that attempted to form. Given how quickly life appeared once stable conditions were established, some researchers have concluded that life must be easy, that chemistry tends to produce self-replicating systems given the right raw materials and energy sources, and that the universe is full of worlds on which this transition has occurred. But a 2025 paper by physicist Robert Endres of Imperial College London applied information theory to the problem of abiogenesis and argued the opposite, that the spontaneous emergence of sufficiently complex, self-replicating chemistry from disordered molecular mixtures is profoundly improbable under random conditions, and that what we observe on Earth, rapid life after the end of the bombardment, may be the exception produced by extremely favorable initial conditions rather than evidence of an easy and repeatable process. The tension between these two interpretations of Earth's biological early history has not been resolved. We have one example. Everything else is inference and model. And until we find either life or its conclusive absence on Mars, on Europa, on Enceladus, in the atmospheres of Venus, or the habitable zone planets of nearby stars, we cannot distinguish between a universe in which life is common and one in which it is nearly absent. The James Webb Space Telescope will make progress on this question in the years ahead. The Mars Sample Return mission, which will eventually bring the Perseverance rover's cached samples back to Earth for analysis, may say something definitive about Mars, but these answers are still years away. For now, the biogenesis question remains open, and its openness is itself significant. It means we genuinely do not know whether the great filter is the step from no life to life, or the step from simple life to complex life, or some step that lies beyond both. And beyond us, what is clear is that the structure of the Drake equation places different solutions to the paradox in very different moral and practical positions. A filter at the origin of life step or at the eukaryotic cell step is a filter that has already operated on us. We are past it. It is geology, not policy. We cannot change where in evolutionary history we arose, and we cannot alter the improbability of the steps that led to our existence. But a filter at the level of technological civilizations, the level of nuclear weapons, engineered biology, artificial intelligence, resource depletion, or any of the other risks that are currently active on this planet, is a filter that we are in the middle of right now. And a filter of that kind is, at least in principle, responsive to what we choose to do. It is not inevitable. It is probabilistic, and the probability is, at least in part, ours to shape. This distinction matters for how the paradox should be held not as an unsolvable mystery about alien populations, but as a question with practical implications for a species that is currently passing through the most dangerous window in its history. It matters whether the galaxy's silence is the silence of worlds that never produced intelligence, or the silence of worlds whose intelligence burned briefly and then extinguished. If it is the first, we are cosmically alone but safe. If it is the second, we are not alone in the sequence of civilizations that have arisen and faced these risks. We simply have not encountered the others because they no longer exist to be encountered. That second interpretation is the one that most directly connects the Fermi paradox to the choices being made in laboratories and parliaments and technology companies around the world right now, in 2026, on the only planet in the known universe that is currently asking the question. The paradox has an additional dimension that rarely receives adequate attention: the question of detection thresholds and what we are actually equipped to find. The searches conducted over the past 66 years have largely been optimized to detect the kind of civilization we currently are, one that broadcasts in the radio spectrum with signals that travel outward in all directions, detectable from a distance by any receiver tuned to the right frequency. This is the model embedded in the hydrogen line search, in Project Ozma, in all the SETI programs that followed. But the assumption that other civilizations would use radio and would broadcast in ways we would recognize is itself a significant constraint on what the searches can tell us. A civilization that communicates via directed laser pulses between specific known recipients produces no detectable leakage. A civilization that has moved beyond electromagnetic communication entirely using quantum entangled links or gravitational wave encoding, or some technology that we have not yet imagined, would be invisible to every instrument we currently operate. The silence may reflect not the absence of civilizations, but the inadequacy of our detection methods to the actual communication technologies in use. This argument must be taken seriously, but it must also be held in proportion. The search space is large, and even a civilization that has moved beyond radio would be expected to generate detectable infrared waste heat from its energy use, or detectable optical signatures from its construction projects. The total absence of any technosignature in any frequency band remains a fact that is difficult to explain away entirely by appeal to our limited detection methods, though the search is genuinely far from complete. There is a particular quality to silence that changes when you understand what it should be replacing. The silence of an empty room is simply quiet. The silence of a room in which a conversation was supposed to be happening is something else: a presence, a shape, an absence that weighs. The Fermi paradox produces the second kind of silence. It is not the silence of a universe in which nothing was expected to speak. It is the silence of a universe in which, by every reasonable scientific calculation, the frequency bands should be alive with signal, and the solar system should bear the traces of many visitors, and we should be neither the youngest, nor the loneliest, nor the most fragile species in the Milky Way. What we hear, instead, is the quiet of a room that was meant to be full, and the weight of that quiet grows heavier the longer you sit with it. Part 3: Move through the proposed solutions. The rare Earth argument that Earth's precise combination of conditions is so unlikely that complex life is extraordinarily scarce. The great filter in its two possible orientations, behind us or ahead of us. The self-destruction scenarios, with their terrible implication of universality. The dark forest, with its logic of predatory silence. The zoo, the transcension, and the others. Each was examined for what it costs to believe it. None of them came free. That examination is now behind us, and what remains is the question the paradox has been building toward since Enrico Fermi asked it, between courses at the Fuller Lodge in 1950. What does the silence say to us? Here, now, in the 21st century, on this particular planet, in this particular moment in our species' history, the genuinely new angle that Part 4 offers, and the angle the entire preceding story has been building toward, is this. The Fermi paradox is not a question about alien biology or the prevalence of radio signals from distant star systems. It is a question about the developmental trajectory of technological civilizations. It is, in the most direct and unavoidable sense, a question about us, and the answer to the paradox, whatever form it ultimately takes, doubles as a statement about the kind of future we can expect to inhabit. Begin with what the great filters ahead of us orientation actually requires. If the filter is located somewhere in our future, if something eliminates essentially every civilization that reaches our current level of development, then the characteristics of that something can be inferred from the final silence. It cannot be purely external, in the sense of a physical catastrophe, like an asteroid impact, because those events are random, and some civilizations would survive them by sheer geographic distribution across multiple worlds. An asteroid that destroys a single inhabited planet leaves the civilization's colonies unharmed. If any civilization in the galaxy's 10 billion year history had reached the stage of multi-world colonization, and the colonization timescale argument suggests that any civilization that tried would have succeeded, given the time available, then random external catastrophes cannot serve as the universal filter. The filter, if it is ahead of us, must be something that strikes civilizations before they distribute themselves across multiple worlds. It must be something that operates during or before the phase of planetary confinement, while the entire civilization is still concentrated on a single fragile rock. This is the core of why the self-destruction scenarios are taken seriously despite their bleakness. Nuclear weapons, engineered pandemics, runaway climate alteration, misaligned artificial intelligence. All of these are risks that civilizations encounter while they are still confined to their home world, before they have achieved the redundancy of multi-world existence. And the window during which these risks are most acute corresponds to the window in which the civilization is technologically powerful enough to produce them, but not yet technologically resilient enough to survive them. It is the window we currently inhabit. We have the weapons, we have the biotechnology, we have the artificial intelligence. We have not yet colonized another world. We are, by this analysis, inside the danger zone, and the silence of the galaxy is the statistical testimony of what typically happens to civilizations in the danger zone. The most recent scientific work has added new dimension to this concern. In 2024, astrophysicist Michael Garrett published an analysis in the journal Acta Astronautica, arguing that the development of artificial superintelligence, if it proceeds along trajectories similar to those currently projected, could limit the communicative lifespan of technological civilizations to a few centuries, at most far shorter than the galactic timescales on which SETI surveys operate. If artificial intelligence, once it surpasses biological intelligence, tends to reorient civilization in ways that either eliminate its biological creators or simply cease the kind of electromagnetic broadcasting that we have been searching for, Then civilizations might pass through our current detectable phase and then go silent in a matter of decades or centuries. The silence would not mean they are extinct. It might mean they have transformed into something we do not recognize and cannot detect. But whether they are extinct or transformed, the observable universe they leave behind looks the same: empty, quiet, without signal. Garrett's analysis does not resolve the paradox. No single analysis does, but it illuminates the way in which the paradox's darkness has deepened over the past several decades as the list of technological risks available to an early industrial civilization has lengthened. Every time our own civilization develops a new class of powerful technology, the list of things that could go wrong with that technology, the list of potential filter candidates grows longer. Nuclear weapons entered the list in 1945. Recombinant DNA technology entered the list in the 1970s. Advanced machine learning entered the list in the 21st century. Each addition to the list is a new candidate for the thing that stops civilizations before they can spread across the stars. And each candidate, examined honestly, has plausible mechanics that could make it nearly universal. This is where the Fermi paradox passes from being a puzzle about astronomy into being something closer to a mirror. The silence is not only informing us about the fate of other civilizations, it is informing us about the range of futures available to our own. If the filter is ahead of us, we are already past the point where our existence is in question. The question now is whether we are the exception or whether the pattern of the galaxy repeats itself in our case. And the answer to that question is determined not by what happened on 1,000 dead worlds, but by what we choose to do on this living one. Nick Bostrom's argument about the discovery of extraterrestrial life connects to this directly. His essay argued that a barren Mars would be good news. It would leave open the possibility that the filter lies somewhere in life's origin or early evolution, safely behind us, and that our strange convergence of lucky circumstances placed us on the rare side of that filter. A living Mars would be bad news. It would tell us that life is not the hard step, that life is in fact quite easy, and that the filter must therefore be located somewhere in the long sequence of steps between single-celled organisms and interstellar civilization, a sequence we are still in the middle of traversing. As of June of 2026, Mars has yielded no confirmed signs of life, past or present. NASA's Perseverance rover has been drilling samples from the Jezero crater, an ancient river delta where conditions are thought to have been favorable for microbial life roughly 3.5 billion years ago, and caching them for eventual return to Earth by a future sample return mission. The samples have not yet been returned. The analysis has not yet been completed. Mars may still be barren. It may contain the chemical shadows of ancient biology. We do not yet know. But the question Bostrom asked about Mars in 2008 has not been answered, and it has not lost any of its sharpness in the intervening 18 years. What has changed in those 18 years is the precision with which the paradox can be examined. We now have confirmed counts of thousands of exoplanets. We have direct atmospheric characterization of several nearby rocky worlds. We have the James Webb Space Telescope, whose infrared sensitivity can, in principle, detect atmospheric biosignatures, oxygen, methane, water vapor, in anomalous combinations on planets orbiting nearby stars. We have fast scanning dozens of target systems at unprecedented sensitivity, and across all of these instruments, across all of these targets, across all of the expanded observational capacity of the past 2 decades, the result remains the same. as it was in 1960, when Frank Drake aimed his 85-foot dish at Tau, Ceti, and Epsilon Eridani. Nothing confirmed. The universe has not broken its silence. This consistency across expanding observational capacity is itself significant. When the search was small, the silence was easy to explain as a limitation of our tools. The tools are no longer small. The James Webb Space Telescope can detect carbon dioxide in the atmosphere of a planet hundreds of light years away. FAST can detect a radar signal equivalent to an airport radar beacon at a distance of thousands of light years. If the galaxy were populated with civilizations broadcasting at anything approaching our own current signal output, we would expect to have detected some signature of that activity by now. The silence in 2026 is not the silence of insufficient listening. It is the silence of listening carefully and hearing nothing. This does not prove that nothing exists. It does not prove the filter is ahead of us. It does not confirm the rare Earth hypothesis or any of the self-destruction scenarios. The Fermi paradox remains, as it always has been, unresolved. What has changed is the weight of the silence. 76 years ago, Fermi asked the question at a lunch table, and there was laughter, and the laughter was appropriate because the answer might have been simple. We simply hadn't looked yet. We have now been looking carefully for 66 years. The silence has accumulated. It has become a fact about the universe, rather than a gap in our knowledge, and that fact is what we are now left with. Here is what the fact says. In its plainest form, every civilization that has ever existed in the Milky Way, if any existed, has either remained undetectable by all the methods we have used to search, or failed to expand beyond its home system, or never produced the kind of electromagnetic signals we have been searching for, or never existed in the first place. The observable universe, as we have examined it, contains one confirmed, intelligent, technology-building, signal-generating species. This one, the species that first achieved a controlled nuclear chain reaction beneath the stands of a university stadium in 1942. The species that launched its first satellite in 1957. The species that set foot on another world in 1969 and sent robotic emissaries beyond the boundary of the solar system by 1977, the same year the most tantalizing radio signal in the history of SETI was received, annotated with a single word, and never heard again. This species, with its 76-year-old unanswered question and its expanding but still finite collection of instruments, is the only confirmed voice in a galaxy that by rights should have been full of them long before our sun was born. That is a genuinely extraordinary fact. It is also a fact that carries a double edge. On one side, it might mean we are rare. It might mean that the path from chemistry to consciousness is so difficult, the conditions so specific, the lucky breaks so numerous and so improbable, that our existence is a statistical miracle unlikely to have been replicated anywhere else in this galaxy. On the other side, it might mean we are next. It might mean that civilizations do arise here and there across the Milky Way and burn briefly with the light of their technology and then go dark, not because they were eliminated from outside, but because they eliminated themselves from within, or transformed into something unrecognizable, or hit a wall in their development that nothing in their biology or culture equipped them to navigate. On this side of the edge, our extraordinary fact is not evidence of our rarity. It is evidence of our precariousness. The paradox does not tell us which side of that edge we are on. It cannot. The evidence is the same on both interpretations: silence, consistent and total, and the difference between them is not observable but predictive. The rare Earth side predicts that we will search the universe with ever better instruments and continue to find nothing. The filter ahead side predicts that our civilization will eventually encounter the thing that has stopped all the others, and that our continued existence is not guaranteed. Both predictions are consistent with every observation we have made so far. Both will remain consistent with future observations for some time to come. The paradox does not resolve, it deepens with information. What the paradox does offer, and this is the genuinely new angle that Part 4 brings, distinct from all the proposed solutions surveyed in Part 3, is a perspective on what it means to be alive at this specific moment in the history of this specific civilization. We are, by any honest accounting, at a peculiar juncture. We are technologically powerful enough to have destroyed ourselves multiple times over in the course of the past century, and we have not yet done so. We are scientifically sophisticated enough to understand the silence of the cosmos and to grasp its possible implications for our own survival, and we have not yet internalized those implications in the way that they arguably deserve. We are biologically parochial enough to be operating from evolutionary instincts shaped for a small group social environment on an African savanna, while wielding technologies that operate at the level of global systems and existential risks. Every civilization that has ever arisen, if any have arisen, has presumably faced some version of this mismatch. The gap between the scale of the risks that advanced technology creates and the scale of the cognitive and cultural apparatus that the biology of intelligence tends to produce. The mismatch is not destiny. Nothing in the structure of the paradox requires that we fail to navigate it. The filter is not necessarily in our immediate future. Humanity may be among the rare civilizations that successfully makes the transition from planetary confinement to multi-world existence, building the redundancy and distributing the risk enough that no single catastrophe can eliminate us. We may develop the governance structures to manage nuclear weapons and biotechnology and artificial intelligence in ways that no other civilization has managed, or that all the other long-lived civilizations have managed. On whichever interpretation of the silence assigns them a long lifespan, the paradox does not foreclose any future. It only places the futures in their proper statistical context, one that demands attention rather than comfort. There is something that might be called a moral topology to the Fermi paradox, a shape to what it requires of us, if we take it seriously. It requires that we acknowledge our precariousness without catastrophizing it. It requires that we hold the silence as information rather than dismissing it as the result of insufficient looking. It requires that we understand our longevity as neither assured nor impossible, but as something that depends, to an extent we cannot fully specify, on choices being made now and in the coming decades. It requires, perhaps most fundamentally, that we recognize the significance of the moment we inhabit, not because we are special in the cosmic sense, not because the universe cares about us, but because we happen to be the only confirmed intelligence in this region of the galaxy that is currently in a position to do something about any of this. We are 76 years into a question that has no comfortable answer. The silence that Enrico Fermi pointed at in 1950 has only grown deeper and more precisely measured as the years have passed. The exoplanet surveys have confirmed that the raw material for life is everywhere. The SETI searches have confirmed that detectable signals are nowhere. The James Webb Space Telescope has begun examining the nearest potentially habitable worlds and found no trace of biology. The universe, as we observe it, contains one species that has reached the level of complexity required to ask the question of where everyone else is. That species is awake. It is looking at the sky and finding it dark. It is running the numbers and finding that the darkness is strange. It is examining the proposed explanations and finding that none of them comes without a price. It is sitting with the question that a man asked over lunch between courses, not because anyone expected an answer that afternoon, but because the question, once asked by a mind of that quality, could not be put back down. The silence continues. The instruments are pointed outward. The data is accumulating, and somewhere in the span between the asking and the answering, a span that may outlast everyone now alive, a span that may span generations of scientists who will build better telescopes and send better probes and scan more stars at more frequencies with more sensitivity than anyone now living can fully imagine. The universe may or may not eventually choose to speak. Until it does, we are here, alone in the way that can only be confirmed by absence, uncertain in the way that only insufficient data can produce, and aware in the way that only a species that has asked the right question at the right moment can be. The silence of the cosmos is the loudest thing we have ever heard. What it is telling us, we are still learning how to listen for. The way species relates to an unanswered question tells you something about what kind of species it is. A species that dismisses an unanswered question because the answer is not immediately useful to its survival is one thing. A species that keeps the question alive across decades, that builds more sensitive instruments and launches them into space and trains entire generations of scientists to refine the search, that writes papers and holds conferences and argues about statistical methodologies in the service of a question that was asked off the cuff over lunch by a man who was famous for asking impossible questions. That is something else. It is, among other things, a species that has a relationship with the very long term, a species that is capable of holding a question for 76 years without an answer and not giving up on it. Whether that capacity is sufficient to navigate the dangers that the paradox implies may be waiting for us. That is an open question, but the capacity itself is remarkable. Consider what the search has actually cost. Project Ozma used a single antenna and a small team of volunteers for a few months in 1960. The Allen telescope array cost roughly $50 million to build and operates at a fraction of the cost of a military satellite. The SETI at Home project extracted hundreds of millions of hours of computing time from ordinary people around the world, voluntarily donated. The FAST telescope in China, while built primarily for other radio astronomy purposes, dedicates observation time to the search at no additional cost. The James Webb Space Telescope, which costs $10 billion to build and launch, was designed for a range of astrophysical purposes, of which the search for biosignatures is only one component. The total investment of resources in the explicit search for extraterrestrial intelligence across 6 decades and across many different national and institutional contexts is modest compared to almost any other major scientific enterprise. It has been sustained not by the expectation of an immediate practical return, but by something more difficult to quantify, the genuine desire of our species to know whether we are alone. That desire is itself a fact about what we are. The philosophical dimension of the paradox, which is where Part 4 has licensed to go, as Parts 1 through 3 deliberately did not, is not separable from the scientific one. The science tells us that the sky is silent. The philosophy tells us what the silence implies about the kind of universe we inhabit and the kind of choices available to us. And the two are not in conflict. The silence is a fact. What we make of it is a choice. Here is one way to hold it. The universe is approximately 13.8 billion years old. The most distant objects we can observe are tens of billions of light years away, separated from us by a void that light has been crossing since shortly after the Big Bang. The galaxy we live in is 10 billion years old and contains between 100 and 400 billion stars. We have been technologically capable in the modern sense, capable of radio astronomy, capable of nuclear energy, capable of spacecraft for less than 1 century. Our entire recorded history spans about 6,000 years. Our species, in its anatomically modern form, has existed for roughly 300,000 years. In the context of the universe's age, we are a phenomenon so recent that the universe, if it were a person, would not yet have had time to blink since we arrived. And in that blink, in that sliver of cosmic time, during which we have existed and asked questions and built instruments and looked outward, we have found no one, the universe that was here before us. Through all the long billions of years in which other stars were forming and dying and other planets were cooling and evolving, left us nothing we can read as the record of any other mind. Perhaps nothing was there to leave that record. Perhaps we are genuinely the first, not just in the Milky Way, but in a much larger region of the observable cosmos, to reach the point of asking the question. Perhaps the conditions that produced us are so specific that we are separated from any other intelligence, not by a few thousand light years, but by billions of light years, by distances that make communication impossible within any human timescale, by a cosmic loneliness so vast that it stretches beyond anything the word loneliness was evolved to describe. If so, the universe is full of matter and energy and time and physics, and it has been playing out in silence for billions of years, and we are the first arrangement of that matter and energy that has ever looked at the sky and wondered why the sky is silent. That is a genuinely vertiginous thought, or perhaps there are others. Perhaps the silence reflects not rarity, but filter the consistent elimination of intelligent life at a stage we have not yet reached. In this reading, the history of the universe is not a history of matter slowly becoming aware of itself through us alone. It is a history of matter becoming aware of itself repeatedly in many places and then going dark repeatedly, for reasons that remain consistent enough across all those independent histories to produce the same outcome every time. A civilization that lasts long enough to build technology then fails to last long enough to use that technology to escape the dangers it creates. On this reading, there have been many voices. We simply cannot hear them because they are extinct, or because they were young and cautious like us, or because the thing that silenced them has not yet silenced us, but is still out there, ahead on the road, waiting. Neither reading is comfortable. Both are honest, and the uncertainty between them, the inability to determine with the evidence currently available, which is correct, is not a failure of science. It is the appropriate epistemic state for a species that has been looking for 66 years with good instruments at a galaxy that may require centuries more of looking before it yields its answer. What we can say, without overreaching the evidence, is this: the universe is very old and very large. The opportunity for intelligence to arise has been available for a very long time, and the most careful search we know how to conduct has returned no confirmed evidence of any intelligence other than our own. That is the data. Everything else is inference, however carefully reasoned. The inference that most squarely confronts us, the one that connects the cosmic silence directly to the choices being made on this planet right now, is the inference that something about the transition between technological, young civilizations and mature, multi-world, long-lived civilizations is extremely difficult. Not impossible, perhaps, but difficult enough that the record of the galaxy suggests very few or perhaps no civilizations have successfully made it. We are, if this inference is correct, at the threshold. We are the civilization that is young enough to still be confined to one world, powerful enough to destroy that world, and uncertain enough about our own trajectory to be genuinely unsure which side of the threshold our particular path leads to. The Fermi paradox ends there, not with an answer, but with that recognition. It ends with the understanding that the question Enrico Fermi asked in 1950 was not really about aliens at all. It was about the durability of intelligence. It was about what happens to a species that develops the ability to ask large questions and build powerful tools and look outward at the cosmos and find it empty. It was, in the deepest sense, a question about whether intelligence tends to survive its own ingenuity. The silence is the universe's current answer. Whether that answer is temporary, whether some civilization somewhere is still out there and our instruments have simply not found it yet, or whether it will one day be broken by a signal that changes everything no one alive today can know. What we know is that the question is asked, and that the asking is not trivial, and that the species doing the asking is the only one, so far, that we have confirmed exists. That fact is at once the most humbling and the most galvanizing truth that the paradox delivers. We are here. We are looking. We are, as best we can determine, alone in the looking, and the universe, in its great age and its great silence, is not telling us what to do about it. It is only waiting, as it always has, to see what we do next. There is a particular sentence that Enrico Fermi's companion, Herbert York, used to describe Fermi's conclusion on that summer afternoon in 1950. York recalled that Fermi ultimately said something about the distances to the next location of living beings possibly being very great, and that as far as our galaxy was concerned, we might be living somewhere in the sticks, far removed from the metropolitan area of the galactic center. It was a characteristically Fermi-like way of putting it, precise, slightly wry, comfortable with uncertainty. He did not claim the sky was definitely empty. He claimed it was probably very full and very far away, and that the farness was a more tractable explanation than the emptiness. He left the question open in the way that good questions should be left, not with false resolution, but with the honest acknowledgement that the question had been asked and the data was not yet in. The data is more in now than it was in 1950. Not enough to close the question, but enough to make it harder, enough to rule out some of the easy escapes, enough to ensure that we haven't looked long enough is a less satisfying answer in 2026 than it was in 1960, because we have looked considerably longer, with considerably better tools, and the sky has not flinched. The question is not going to be answered this year, or possibly this century, but it will not be unasked either. And in the space between the asking and the answering, which may be the space in which we spend the remainder of our existence as a species, however long that turns out to be, the question has a function. It keeps us honest about what we are and what we do not know, and what the universe has not yet told us, and what our own behavior in the world might be saying to any intelligence elsewhere that might be listening. The Fermi paradox is, among everything else it is, a reminder that what we do here matters more than it would if we were embedded in a cosmos full of other voices to absorb the consequences of our choices. If we are alone, then every choice we make is the only choice of its kind being made in this galaxy at this moment, and the stakes of getting those choices wrong are correspondingly absolute. Sleep softly, stargazer. The cosmos keeps its silence tonight, and so may you.